Hi. Hi, thank you everyone for being here. I'm Xiangyu from University of Toronto. We study at HotCRP. Today I'm going to present the paper EvoCrawl, Exploring Web Application Code and State Using Evolutionary Search. EvoCrawl is a black box scanner detecting vulnerabilities in web applications by interacting with the browser on the client side. The black box here means the scanner has no access to the source code. We designed it to be black box because we think it would be more generalized and not restricted by the programming type of web applications, since they have been developed in many different languages such as PHP, JavaScript, or Ruby or Rails, etc. Previous studies has shown that the performance of a crawler largely depends on how many code it can cover on the server side. Since we are operating in a black box way, the question now becomes how can we improve code coverage for a crawler with no access to source code? We try to do this by designing the crawler to crawl on as many pages as possible. Also, it has been demonstrated that the number of crawl pages is actually heavily influenced by the application state, which means certain pages can only be crawled when the application are in this state. The application state here typically refers to the data stored in the application. Take HotCRP as an example. The paper reviewing page and the paper editing page can only be crawled by the crawler after the crawler successfully create a paper submission first. After create a paper submission, the crawler can successfully transition the application from a state that has no paper to a state that has a paper. So how does a black box scanner change the data stored on the server? How does it inject inputs to the application? Since the crawler is operating on the browser side, the most common method now is submitting HTML forms. However, submitting HTML forms can be pretty hard. Consider this small example here. This is a project management web page by Kanboard. If you click on this plus sign in the blue box, it will open a pop-up window. While in the meantime, the pop-up window will block the elements above this window, the elements in the upper side of the slides. So how do we submit this form? So for us, it's pretty easy. We just click on the plus sign and then fill in the title field. Finally, we click on the save button. Then we've completed the task. However, for a crawler, to find this sequence of combination is pretty hard, since it needs to find the right combination in those many elements. And even for this single page, and for a simple sequence that only contains 3 interactions, there are around 30,000 possible combinations, since there are approximately 33 elements on the page. So it would be good for actually executing all those 30,000 combinations can cost a lot of time for the crawler only on this one page. So to increase the performance of the crawler, increase the speed of the crawler, we need to find a way to avoid the crawler spending some time on some sequence that is not worth to explore. Here is a part of the possible sequences here. If you still remember, this pop-up window will block the elements of the original web page, the elements in the black box. So actually, there's no meaning if you click on the plus sign first and then also interact with the elements in the black box. So if you could find a way to avoid sequences with those bad orders, instead guide the scanner to explore sequences that with good orders here, you could save the crawler a lot of time and therefore increase the performance. To summarize a little bit, we kind of need a way to get the scanner to explore sequences that with good orders. After finding this sequence, should we stop it here? Should the crawler stop at here? Apparently not, right? Because there are many other input fields on this form as well. We also want to submit them because form submission with different combination of inputs can possibly trigger different codes on the server. They can also be possible injection points for injection-based vulnerability payload as well. So now the question is, how do we find a longer sequence with more inputs from this one small sequence? How do we derive a blue sequence from the gray sequence? How do we gradually add more input fields to a shorter sequence and then finally inject more inputs to the database? And in the meantime, avoid certain elements such as cancel button or elements that require values cannot be inferred by crawlers. since they can prevent the firm from submitting. Now, after a summary of the motivation we need a way to effectively generate sequences that preserve good orders. We also need a way to generate new sequences from the sequences found to already have good orders. That's why I want to introduce you to evolutionary search and dependency tracking. We choose to use diversified evolutionary search because we aim to explore diversified states of the application, thus we need diversified sequences. The fitness function and the crossover operation of the evolutionary search help us to identify sequences with good order and generate good sequences. So what sequences are considered to have good order? We tend to reward on sequences that can inject inputs into the database or fill in more input fields, or in the end, trigger JavaScript events. All these three operations can help the crawler to transition application into diverse states. Also, trigger JavaScript events can enable new elements on the web pages and exposing possible new links on the page as well. We also want to punish on sequences that interact with block elements. Since they didn't follow the order and there's no meaning to interact with them, we'll just waste the crawler's time. Now we have a fitness function help the crawler identify which sequences are considered to be good. Now we need a way to generate potentially new good sequences based on those sequences found to be good. That's why I want to introduce you to the crossover operation. It's just concatenate parts of two sequences together. The benefits of this is can introduce diversity into sequences while partially maintaining the order. Consider this two small examples here. This is just like two different sequence interactions. The gray sequences is just to fill in the title field, is the gray one element, and then click on the gray 2 save button. And the blue sequence is just fill in many different input fields, but they never hit the save button to submit them. So this way you have two different parents. You fill in the title field, which is gray 1, and you click on the gray 2 save button. This way you have like one input inject into the database. And you have this parents B, which you fill in many different input fields, but never click on the save button, so they never be injected. By crossover those two sequences, you have a new sequence, you fill in more different input fields, and finally click on the gray 2 save button. This will result in more input injections and will transition the application into a different states. Now we have an evolutionary search and can help us generate good sequences from good sequences. But we also kind of need a way to let a crawler generate sequence with good order from scratch. So that's why we want to introduce you to dependency tracking. We consider the dependencies to exist among elements when interaction with an element change the status of some web elements, some other elements. So if you still remember, if you click on the plus sign, there will be a pop-up window, and the title and save elements are part of them. So the title and save elements are dependent on the plus sign, which means in the sequence of interaction, the title and save elements should follow the plus sign elements as well instead of others. So to summarize what we have now, we have evolutionary search and dependency tracking. Those two mechanisms enable us to generate good sequences from scratch. Also enable us to generate longer sequences from shorter sequences as well. By executing those sequences, we can transition the application into different states. And while the application into different states, we can possibly have more chances to crawl on more pages and achieve better code coverage on the server side. To really evaluate the vulnerability detection ability on the EvoCrawl, we integrate IDOR and cross-site scripting vulnerabilities detectors into it. Details are in the paper. We also support future integration of other vulnerability detector. So to evaluate it, we measured 3 different metrics. The first one is code coverage. The second one is firm submission. And finally, we measured the vulnerability detection ability. For code coverage, we compare EvoCrawl with Black Widow, Jack, and CrawlJax. And for firm submission, we compare EvoCrawl with Black Widow. Finally, we collect the number of vulnerabilities found by EvoCrawl. Here is our results of code coverage. So the blue bar here typically shows the unique lines covered by EvoCrawl on 10 different applications. And the red bar shows the unique lines covered by the other baseline on 10 applications. The orange bar shows the common lines covered by both crawlers. We can see in average, EvoCrawl cover 1.5 times lines of code compared with other baselines. We also measure the number of firm submissions. We measure by count the total number of forms submitted by EvoCrawl and also common forms submitted by both crawlers and unique forms submitted by Black Widow. In average, we submit 4 times more unique forms compared with the baseline. Also, for vulnerability detection, EvoCrawl finds 3 different IDOR endpoints, and all of them actually requires the crawler to transition the application into different states. So take this particular example to illustrate. The crawler needs to first upload a private picture, then it can test whether the access controllability of the page. So this requires the crawler to transition the application from state 0 to state 1 by uploading the private picture. Also, EvoCrawl find 5 different cross-site scripting vulnerability across 3 different applications. Details can be found in the paper. Also, many of them require certain state transitions. I want to illustrate on one certain example. It's stored cross-site scripting vulnerabilities. So actually, to inject and execute these cross-site scripting vulnerabilities, the crawler needs to transition the application into 4 different states. The first, you need to inject the payload. The crawler needs to add a new decision type. And then it needs to create a paper submission. Finally, to execute the payload, you need to assign a new decision type to the paper. So to actually inject and execute the payload, the crawler needs to transition application into many different states. Here's our conclusion. We think using an evolutionary search algorithm with dependency tracking enables a scanner to transition the application into diverse states. Thus achieves greater code coverage. Also, evolutionary search can get the crawler toward favorable objectives, such as form submission, input injection, and elements that trigger JavaScript events. Thank you very much for listening. Don't forget to check our GitHub repo. I'm happy to take any questions.
If you have questions, please walk to the mic to ask your questions.
Hello. Very great presentation. Loved it so much. I was wondering, did you check some specific cases for attribution of how and why the specific algorithm achieved much more coverage, like for the case you just showed?
Oh, yeah. We have an ablation study for the dependency tracking mechanism, which we run the evolutionary search along without dependency tracking and compare the results with the entire EvoCrawl. And you can check our results in the paper, and just actually dependency tracking help a lot on the code coverage during the evaluation.
Cool. I'll definitely do it. Thank you so much.
Thank you.
Any other questions? Okay, I have a question. So you mentioned that there are some dependencies between some elements. Could you elaborate more on how do you differentiate the elements from those who has dependencies and from those who doesn't have dependencies?
So we capture dependency by using an API of the JavaScript. So if an interaction on an element change the DOM and then expose new elements on the web page, we think there's a dependency of that interaction with the elements shows on the web page. That's how we think there's a dependency among them.
Okay, thank you.
Okay.
Any other questions? Okay, so let's thank our speaker again.